Alright, so in this video, we're going to talk about problem solving, and we're going to talk about how to solve the count primes problem. In this video, we're going to talk over the problem solving process and strategy. We're really going to break down how we actually approach solving problems and a strategy that I like to call the umpire method, and I'll tell you what that stands for later. But really what this is what do you do when you're not sure where to start? A lot of times people problem solve, and they kind of problem solve in their head, and it's kind of this mysterious process where you look at a problem and then the answer eventually just appears to you. And that's great, except for when you need to solve the problem in 45 minutes because you're in an interview. And so you need to make it happen rather than just waiting for brilliance to strike you, right? So let's talk a little bit how we might break down a problem. There's several steps, and it's easy to remember, kind of when you're nervous or when you're really stuck, if you have this acronym, umpire. So U starts for understand. That's the very first step. We want to clarify what the interviewer is asking for. What we want to do is then kind of see, have we looked at similar problems in the past before? Have we ever seen a similar problem like this? What did we do to solve it in the past? Or what was kind of the patterns that we were going to do? Plan, which is where after you've gone through like your understanding and your match phase, you kind of go through the data and write down the steps that you as a human take to get the answer. And so you want to make a plan first. And this is all far before you ever get to coding, thinking about what data structures you want to use. Don't worry about all that stuff right in the beginning. What you really want to do is focus on what is the problem. Have I seen this stuff before? Is there any experience I can bring to the table here? And then you want to make a good plan. Because translating a plan into syntax is much easier than trying to solve the problem with code, right, in your brain. Then after we do all of that, we implement and we write the code. And then we will review the code and kind of go through it with our minds and be the interpreter to test our solution with several test cases. At the very end of all that, that's when we really get into the space and time complexity of the solution, and then we can do stuff like ask questions about what can we do to change our solution to make it faster or take up less space or be more memory efficient, that kind of thing. But the big takeaway here is that you have to build understanding. Sometimes that is what you're building. Just sitting down and typing is not the solution. You don't get to a solution until you have a full understanding of the problem and what each individual step is that you're trying to solve. So let's take a look at the prompt, and let's ask ourselves a few questions about this prompt that'll help us to really break the problem down. First question is just, what is the prompt itself? You're going to have to take a look at this prompt multiple times in order to really get all the details out of it. Second question you should ask are, what are the key actions that we need to take? This is kind of translates to the return value, but it's also often there is a method that is described in a prompt, and so you need to understand what is the method that I'm supposed to use and what are the actions I'm supposed to take. Now the key action here is counting. You want to count the number of prime numbers less than a non-negative number n. So that's counting, not returning a list, right? And that's an important distinction, because if your interviewer is looking that you understand how to read problems very detailed, they're going to want to know that you're going to, notice the difference between count and return a list of. We also need to just take a moment to kind of recognize what is it that we're going to be given as an input. Now, you'll see it's a non-negative number n, right? There's a couple of pieces of information there. What data type is it? It's a number. It's not coming in as a string. And because it's stated in the prompt, we can kind of make some assumptions here. In an interview, you'll want to ask these assumptions out loud just to register that you know that these assumptions are being made. But we know that our number is coming in non-negative. We know that it'll be a number and not a string. We're not going to get a null value. or, so there's a lot of information there that you're getting, but you want to make sure by asking this information. And then we want to look at the output exactly, right? Take those key actions, count the number of prime numbers. And then we think, okay, what is it that our problem actually has to return? And that's the number of prime numbers. It's going to be a single number less than the prime, right? And so we know it's going to be a number that we return, right? Those are the questions that we need to ask ourselves in order to really fully understand the problem. Now, and also, what is the format of the output? Now, you will see this come up more in more complex problems. This count, that's the format. It's as a number, as a count of. But as a string or something else that you might have in another problem, you need to know the exact format that the output is supposed to come in. So the next thing that you'll want to do is you'll want to think about, okay, have I seen problems like this before, right? If you've ever dealt with prime numbers or trying to figure out whether a number is prime, that's what you want to try to call up in your memory, right? And then, here we know that prime numbers kind of have a specific set of operations, right? In order to determine whether a number is prime, it can only be divisible by 1 and itself. And so we know that there's going to be some division involved in checking to see whether a number is prime. Determining primality, that's one of the problems that you need to kind of have in your mind whenever you're going to go into an interview, because it's one of the more common themes. It might not be this exact small problem, it might be some other thing where determining primality is involved, but you can just match from having done this problem, which is part of the reason why we're having you go through these problems. So prime factors, that's another thing. Determining the prime factors of a number, that's another key component to this. And then keeping track of the prime numbers that you've already found, right? We're counting them, so we can't just determine if a number is prime and throw it away. We need to keep track. All right. So the next phase, once you've kind of loaded all of that stuff in, once you've thought about all those things, is you want to create a plan. You know that you've got to find prime numbers. You know you're going to find a count, right? And so at this stage, what's crucial to do is draw it out by hand. Some examples that are going to work with the prompt, right? And so what you'll have to do is decide on what n is. You'll want to pick a small n. Don't try to do it for 100, Also don't try to do it for 1 or 2. Usually in most prompts, you want to pick some data that has enough for you to go through a few iterations, but not so little that it's just 1 or 2, because those cases are often special cases. You want to mentally determine the answer, right? So you may know that under 10 there are 4 prime numbers, 2, 3, 5, and 7. And so if you already know that there's 4 prime numbers below 10, you could pick 10 as an n. And then, if you know that there's, I think, 8 under 20, if you already know what the answer is, then you can check to see that your plan actually does what you want your plan to do. Then it really helps at this point to write the data out and draw a picture. Interviewers want to see this. You'll need to use it in problem solving for the rest of your career. Drawing out the problem so that you can solve it is a key step that even senior developers do all the time. And then you want to talk out loud about the decisions, especially if there's another person in the room. Don't just stare at your picture. Talk out loud over the process, right? And try not to skip steps. As a human, we tend to skip steps, and so try to think robotically about the process that you're doing. And then as you do that, just write your steps down. Describe what it is that you as a human being are doing, and that'll make it much easier for you begin to make a plan about how to tell the machine what to do. And then you want to check it over again. Make sure your plan will work for a larger n or a different case. So let's do that together by hand. So I've got, 1 through 10 here, right? And so we'll imagine that our input is 10. And what I need to do is determine how many prime numbers there are under 10. Now 1 does not count because it's 1. Everything's divisible by 1. So nobody counts 1. But 2 is only divisible by 1 in itself. So it is a prime number. So we'll mark 2 as prime. Now 3 is not divisible by anything but 1 in itself. So 3 is a prime number. So we've already got 2 primes. 2 and 3. Now 4. 4 is divisible by one of our primes, by 2. So we can just, cut it out. 5 isn't divisible by anything but 1 in itself. So 5 isn't divisible by anything but 1 in itself. So we can mark that as prime. Now 6 is divisible by both 2 and 3. So it's not a prime number. 7 is a prime number. It's not divisible by anything, by 2, by 3, by 5. Now 8 is divisible by several numbers that we've already seen. We've seen that we can tell that it's divisible by 2 because it's even, but it's also divisible by 4. And so 8's got a bunch of different divisors. 9 is divisible by 3, and so it's not a prime number. And 10 is, of course, divisible by 1, or by 2 and by 5. So let's think about that again. Let's go through it and think about this as a process, right? And break it down. So we're skipping 1. 1 doesn't count. So we're kind of going to move on to 2, and we're just thinking about 2. And we can mark it as a prime because it's not divisible by anything. And 3 as well, not divisible by anything. It's not divisible by 2, and of course we don't have 1 to compare it to. 4, once we get to 4, what are we really dividing 4 by? We haven't really asked ourselves that. But what we do is we look at numbers lower than 4, and we try to see if they're divisible by anything. So we start with 2, and 4 is already divisible by 2. So we don't really have to check to see if 4 is divisible by 3. We can just stop once we've found one number that it's divisible by. So let's look at 5. 5's not divisible by 2 or 3 or 4. But something to notice is that if something were divisible by 4, it would follow that it was also divisible by 2. And so we don't really need to ask ourselves, are things divisible by 4? Because we'll already eliminate them by having them been divisible by 2. We can look at 7, or 6, right? And 6 is divisible by 2, so we don't have to check 3, even though we know in our minds that 6 is divisible by 3. We really only want to start with, I think, our first prime. And then we'll check 7, it's not divisible by 2, not by 3. We know that we don't have to check 4. We'll check 5. Nope, not divisible by 5. Okay, so it's prime. We don't have to check 6, because if it were divisible by 6, it would be divisible by 2 and 3. So we don't have to check that. Now if we move on to 8, we'll check it with 2. And again, 8's divisible by 4, but it doesn't matter because it's divisible by 2. And we really only need to know if a number is divisible by any other number. We get to 9, we'll check 2. Nope, it's not divisible by 2, but that doesn't mean it's not a prime number. But that doesn't mean that it's a prime number, because once we check it with 3, 9 proves to be divisible by 3. And so it's not a prime number. And then when we get to 10, we find that it's divisible by 2. So let's get deeper into that process so that we know what the steps really are. It looks like we're going to go number by number. Really, we're going to start with 2 because 1 never counts. No matter what n is, 1 will never really count. So we'll start with 2 every single time. We also know for sure that 2 is a prime number, and we know that 3 is a prime number. So as long as n is 4 or less, we can just know that 2 and 3 are there. So we can kind of keep track of just noticing these things, right? So let's go by hand. Once we get to the higher numbers, you'll start to see this process shake out. So we know 2, 3, we know 4, 5, 6, 7, 8, 9, and 10. Let's say we have 2, 3, 5, and 7. We already have our primes, and we're here at 10. We're going to move on to 11. Now, let's try to divide 11 by 2. Nope, doesn't come out. 3, nope, doesn't come out. 5, nope, doesn't come out. 7, nope, doesn't come out. Now, we know that 11 is a prime number, and so we can kind of keep track of all of that. And then we'll go on to 12. We'll check 2, being it's divisible by 2, and so it's not a prime. We'll move on to 13. And so we'll check 2, nope, 3, nope, 5, nope, 7, nope, 11, nope. Looks like 13 is a prime number. 14, divisible by 2. 15, not divisible by 2. Let's check 3, divisible by 3. 16, divisible by 2. 17, not divisible by 2. Not divisible by 3. Not divisible by 5, not divisible by 7, not divisible by 11, not divisible by 13. Alright, so 17 is a prime number. And 18, let's look, not divisible by 2, it's divisible by 2. Alright, 18, divisible by 2, so not a prime. 19, not divisible by 2, not divisible by 3, not divisible by 5, not divisible by 7, not divisible by 11, not divisible by 13, not divisible by 17, and so 19 is a prime number as well. 20 is, of course, divisible by 2, and so it's not. So now we have all these primes that we've found. Let's look at our higher prime numbers. We went ahead and tried to divide 19 by 2 and 3 and 5 and 7, and that's fine, but once we tried to divide 19 by 11, we know that 19 will not be divisible by 11 because 2 times 11 is 22. And so we know that 19 is not going to be divisible by something that is, if it were multiplied by the smallest prime number, it would be too high. So we can kind of stop at a certain point with a number in that, like, if this prime is, doubled or tripled, twice as big, we know that it's not going to be divisible by that number. And so we don't need to check any further numbers that are higher than that, right? In fact, we don't need to check any numbers that are higher than, so far we've found at least half the size of the current number, right? So those are some things that I just noticed about the data by writing it out and going through it and trying to think about how do prime numbers work and what steps do I really have to take here. So the match and plan phase kind of go hand in hand. They happen both at the same time, right? While you're doing the plan, while you're doing the step-by-step, walking through the algorithm phase, you want to look at the patterns that you notice. That's where those optimizations are going to come in, right? You don't have to note them and get them into your algorithm right away. It's just that later, when you're going to go and improve your algorithm after the first one works, that information is what's going to help you to create your best solution. Again, it's not very important that we really get to the most optimum solution on the first guess. It's not about knowing the optimum solutions offhand. It's really about being able to arrive at the correct conclusion. Another step that we want to notice in order to evaluate it later is how did the number of steps change as the input changes? When we added twice the number of numbers to evaluate, how many more steps did I have to go through? Now, I didn't write down these steps yet. What I've done is I've just still kind of gone through, and I know that I can determine the number, right? And so at this point, this is where we would want to write this down.